you learn that light is a wave. Here it is, up and down. So the light in this case has the peak here, and we call this peak a crest. And this valley here, we call it a trough. T-R-O-U-G-H. So what is important about this? Well, the word wavelength. So make sure you understand the definition of a wavelength. And it has this symbol that's called lambda. This is a Greek letter. And it's the distance between two crests. You see here, the distance between two crests, or two troughs, if we have a continuation here. That would be a wavelength. So again, the unit for this is lambda. It looks like an incomplete X. And it would have a unit of meters or nanometers. And the reason why is because the word length, remember, fundamental unit, is in meters or nanometers. So remember, nanometers is 10 to the negative 9 meters, very small, and we're going to get to it. On the other hand, we have something else called frequency. It has this symbol, it's nu, it's pronounced nu, it's a Greek letter, it looks like a V, but it's an N, and it's the number of waves passing a given point per second, and the unit is hertz, or inverse seconds, or S-1. Okay, so let's actually illustrate what frequency is down here. Frequency, imagine we have a line here, and we have point X, and imagine we have a wave. Okay, and imagine you have a timer. You start your timer, and you notice that in 1 second, you had 1, 2, 3 waves, okay, pass per second, or every second. Well, that would be called frequency. So that would be frequency. In this case, it would be 3 inverse seconds, or this inverse second is called hertz, or Hz. So when you hear of a processor, it's called, they have this many megahertz, gigahertz, all that stuff. Again, that means it's a frequency. Very well. So then the question is, what is the relationship between wavelength and frequency? Well, they have an inverse relationship. What that means is that when one increases, so if the wavelength increases, the frequency decreases, it goes down, and vice versa. If the frequency goes up, the wavelength goes down, but it actually depends on the wavelength. So let's look at a simulation here that's better than mine. So if you notice here, I hope you understand why this is low frequency. It has, let's count them, 1, 2, 3, 4, 5, 6, let's say 7 waves. Well, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this one is 7, this one is 13. So you can tell that if you start the timer, you will know that you're going to have more of these waves passing than this one. So let's play it. Let's play this one, and then let's play that one. Okay. So again, you see you have more waves passing in the one down here because it has a shorter wavelength, So this wavelength is, let's say, from here to there. Look how small that wavelength is versus that wavelength. So again, high frequency, low frequency means you have a longer wavelength. High frequency means you have a shorter wavelength. So what is the equation for this? Well, the equation is this. C let's go back here. Electromagnetic radiation travels at the speed of light. And the speed of light is 3.00 times 10 to the 8th meters per second. This is 300 million meters per second, or 187,000 miles per second. It is the fastest thing we know in the universe. There's nothing faster than the speed of light. So here's a question for you. Shorter wavelengths, high frequency light has higher energy. Why? Well, if you go back here, if each carries 1 joule of energy, you know you're going to have more waves, and that corresponds to more energy. So again, more waves means more energy. And of course, you have a shorter wavelength here because you have more waves. You can fit in more waves in this than that one. And again, each carries let's say 1 joule. So you'll have more energy in this one than the one with a longer wavelength and a low frequency. So think about it. That's an important theory. All right, so here's the equation. And here's a quite small basic calculation to do here. It says calculate the wavelength of red light with a frequency of 4.62 times 10 to the 14th second inverse, or hertz. So let's write down our knowns here. So we know we have frequency, and it's 4.62 times 10 to the 14th inverse seconds. It says calculate the wavelength. So that means we do not know lambda, but we must be given something else. Well, C is a constant. Here it is. So therefore, we have frequency, we have the speed of light, that's a constant, and we want to solve for lambda. So let's set up our equation. So we need to solve for lambda, means we divide each side by the frequency. So that means it's going to be C equals C over frequency equals lambda. So let's plug in. Well, C is 3 times 10 to the 8th meters per second. Frequency is 4.62 times 10 to the 14th inverse seconds. And remember, inverse becomes second here because if you recall the math here, or just put the seconds here. So again, you notice that the seconds are going to cancel out. Okay, so 1 over inverse seconds equals seconds. Okay. So if we were to calculate this, we would get 6.49 times 10 to the negative 7th meters. Now, suppose the question is asking you to find that in nanometers. Well, we've done enough of that, so we should be able to do that. So we take that number, 6.49 times 10 to the negative 7th meters. We say we want to calculate this nanometers. Okay, so meters down here, nanometers on the top. We know that a nano is 10 to the negative 9th. So they cancel out. You take negative 7, divide by negative 9. You actually end up adding them, but you actually end up getting this number right here, 649 nanometers. 649. You can move the decimal as well. It works either way. It should not be an issue. So you have 649 nanometers.